Sample problem 16.10. Calculate the pOH of the following aqueous solutions at 25 degrees Celsius: 0.013 molar lithium hydroxide, 0.013 molar barium hydroxide, and 9.2 times 10 to the negative 5 molar potassium hydroxide. So these are all strong bases, right? So let's remind ourselves of the strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. These are all the group 1 metals in the periodic table. And then the group 2 metals, starting with calcium hydroxide, strontium hydroxide, and barium hydroxide. Okay? So those are the 8. I'll try to count this properly. That's 8 strong bases. There is a difference here, and that is that the group 2 metal hydroxides, calcium, strontium, and barium, they each form 2 hydroxides when you dissolve them into water. The effect of that is doubling the concentration of hydroxide. Think of a bicycle. If you have 10 bicycles, but you take the wheels off the bicycles, how many wheels do you have? You would have 20 wheels because there's 2 wheels in every bicycle. Same thing with these hydroxides. When they dissolve, they form 2 hydroxides. So you get a calcium, for example, and then you get 2 hydroxides. So the effect of that is that there's more hydroxide for the given concentration of one of these salts than there is for one of these. Okay, so let's start with A. This is pOH. pOH is the negative log base 10 of the concentration of hydroxide. Okay, just like pH, but it's a measure of hydroxide concentration as opposed to hydronium concentration. So for part A, we have 0.013 molar lithium hydroxide. And since it's a strong base, what that means is the amount of hydroxide that is dissolved into the water is the same as the amount you put into the water of the salt. So if you put in 1 mole of lithium hydroxide, you'll get 1 mole of hydroxide. Therefore, we can go ahead and use this concentration here in our calculation of the pOH. So for this one, the pOH would be the negative log of 0.013. Again, pOH is a unitless quantity, but it's defined based on molarity concentrations. Okay? So 0.013, we want to calculate the pOH. So 0.013, we take the log of that, and then we want to take the negative log, so times negative 1. 1.89. We're going to round that up to a 9 because we only need 2 significant figures, so 8, but the number following the 8 is a 5 or greater, so we'll round it up to 1.89. Okay. There's our pOH. The pOH is a measure of hydroxide concentration, and just like pH, as the concentration of hydroxide increases, the pOH decreases. So the lower the pH, the higher the concentration of hydroxide. So part B is 0.013 molar barium hydroxide. Now this one's put in there because barium hydroxide forms a barium ion, but it also forms 2 hydroxides. So the effect of this is to double the concentration of hydroxide. So the pOH would be the negative log base 10 of not 0.013, but 2 times 0.013, right? Because you get 2 hydroxides every time one of the barium hydroxides dissolves. So that would be the negative log of 0.026. Okay, so 0.026. We're going to take the negative log. So you take the log of it first and then multiply by minus 1. 1.59. Okay, so notice the pH went down compared to part A, even though the concentrations of the ionic compounds were the same. The reason is you get twice as many hydroxides from barium. Part C, the last one, is 9.2 times 10 to the minus 5 molar potassium hydroxide. Okay, so this is a group 1 metal hydroxide. So that means the pOH is just the negative log of that number, 9.2 times 10 to the minus 5. So that's a little bit under 10 to the minus 4. Okay, so 9.2 times 10 to the minus 5. So 9.2 times 10 to the minus 5. Let's put that in decimal so you can see it in decimal, right? 9.2 times 10 to the minus 5. We're going to take the log of that, and then we're going to multiply it by negative 1. 4.04. There's our answer. Now notice that this last one, part C, has the highest pOH, right? It has the lowest concentration of hydroxide, therefore it would have the highest pOH. Okay?